So I set up the oscilloscope here, and I already have the software running. Here you can see the J2161 active splitter, and it has a cable that connects to the AFG in the back of the instrument. It provides the active splitting, which provides the sampling channel, and also one of the S parameter ports that connects to our DUT. For our DUT, I mounted a 1 milliohm resistor on a printed circuit board with connectors. And here on the second connector, we used our second ground isolator, the Picotest J2102B common mode coaxial transformer. Now first, let me go ahead and change the screen just a little bit. We can see the signals at the bottom of the display, but we'd really like to focus on the impedance. So I want that to be bigger in my display, and I can move that. Next, let's take a look at the setup. So here's how this setup works in the oscilloscope. We have two channels that we can select, and we can select any two. Just because of where the cables fell, I thought that channel 2 and channel 8 worked nicely, so I picked those. Most of the setup here is defaulted to where you want it to be. We do have choices of things like spectrum view versus FFT, how many points per decade we want to measure, start frequency, stop frequency. We can control the resolution bandwidth and even the amplitude. I use the setup file because once I set the scope the way I like it, it's kind of much faster for me to just use that as a setup file in order to get the scope set up the way I like it, rather than having to create all the settings again. Now I can preset the scope, and that will get all of these settings applied, and then I can clear the screen. And I'm going to measure this 1 milliohm mounted resistor because I have a simple rule. And the simple rule is that we have to measure something we know before we measure something we don't. And so I just thought this 1 milliohm resistor was kind of a convenient thing for us to measure. Now that we're set up, I can push the run stop button, and the scope is going to set the sensitivities and the way that it wants them, so that the signals maximize signal noise. And you can see it's actually displaying the value here. You can see we have a nice flat plot. You can see it's sweeping pretty quickly, and it's running just about 1.2 milliohms, just under 1.2 milliohms. Well, we have to measure something we know, and I do know that this is about 1.2 milliohms. And the way that I know that is I measured that DC. I forced 1 amp into one of those ports, and I measured the voltage at the other port, and I get about 1.2 milliohms. So I know that this is the right answer. You can see at about 100 kilohertz, the impedance starts to increase, and that's because that is the inductance, the parasitic inductance of our resistor. We went ahead and we were able to make that measurement. It's a nice clean plot. I plotted from 1 kilohertz up to 10 megahertz. But that wasn't the point. The point was for us to be able to do this using a browser probe. So first, we just wanted to make sure our setup works. We had to measure something we know. Now I'm going to connect our browser probe to the same 2 ports. The browser probe uses very low resistance shielded cable. This is Picotest PDN cable. And it has a handle, and it also has detachable heads because these heads come in different sizes. And so this head that I'm using here happens to be a 1206. I don't think the camera's set up for it, but I'm going to go ahead and I'm going to show you a picture of what these 4 points look like. So there you can see the probe. In a close-up view, you can see that the probe actually has 4 pins, 2 signals, 2 grounds. That's 1 signal from each one of the cables, and it's also 1 ground from each one of the cables. And now I have a 1 milliohm resistor. I could mount it on a printed circuit board. In fact, I like to do that only because it's a little easier to keep it from moving around if it's got a little bit more mass. But you don't actually need the printed circuit board to make the measurement. So let's just go ahead and we'll reset the scope to make another measurement, and we're ready to go. And so now I just need to put the probe on it. And there you can see this resistor also is measuring just about 1 milliohm, just a little bit higher, 1.06 milliohms. And we can believe that value because we just measured our known and we got the right answer. And so now we can measure unknowns that are reasonably close to that value and feel confident we got the right answer. Again, you can see there's the parasitic inductance of this resistor. And so measuring a milliohm was actually pretty easy. The scope did it quite well. And we're finished. But what if we want to measure lower than that? Well, we probably can. Here I have a 500 microohm resistor. That's a 2512 size resistor, and so I mounted it on a printed circuit board just because it's a little easier to keep it from floating around. I'm going to try to place the probe without being able to see it very well. We're going to go ahead and we're going to do our power preset, and let's see if we can measure 500 microohms. There you go. The first point is 523, second point is 502, third point is 509. So we're measuring 500 microohms using a browser probe. Move this out of the way. I don't really need to let it finish, but I will because it's going pretty quickly. You can see this has a bit higher inductance than the other resistor did. And there we go. We got to 10 megahertz. Just for fun, let's see if we can go even a little bit lower than that. So I have a 250 microohm resistor here, and I'll try that one too. So we'll do our preset. It's a little bit blind here, but I think I got it. Whoop, it fell off. Let's just start that over. Let's try and go to just a little bit lower resistance. Let's try 250 microohms. That's a little bit challenging because this probe just fits the resistor, but we'll do the best we can. I think I have it placed. That's 260, 268. And there you can see there's the inductive region of the resistor. So we measured our 250 microohm resistor using a browser probe. And we're measuring here from 1 kilohertz to 10 megahertz. We can actually go quite a bit higher than that. Using the MSO6B scope, we can go as high as 50 megahertz using the internal signal generator. We're not really limited to that either. Using an external signal generator like the Tektronix AFG 3000 series, we can go up as high as 250 megahertz.